let's take a look at topic 3.6, logarithmic differentiation. Now, before we get into logarithmic differentiation, we're going to review logarithms because there's a chance that some of you might not have even heard of logs, or maybe you do, but you forgot them. This course assumes no prior knowledge of the log or ln function. So let's begin. Remember that we defined that number e to be this, right? The limit is x approaches infinity of 1 plus 1 over x to the x. And that turned out to be roughly 2.718 or so. And I said it was really important, right? Why was it really important? Well, first of all, the derivative of e to the x was e to the x, right? That's the main reason it's so important. But it turns out, if we consider the inverse function of e to the x, which we call ln of x, ln of x is also very interesting and very important. Now remember, inverse functions cancel out the functions that they're inverses of, right? So we define ln to be the function so that ln of e to the x equals x, and e to the ln of x equals x, right? Again, think of the square root of x squared, right? The square root is the inverse of x squared because it cancels it out, right? The cube root is the inverse of x cubed. We just talked about inverse trig functions, right? Arc sine is the inverse of sine, right? So in other words, we could say ln of e to the x equals e to the ln of x, which equals x. And you could also say that y equals ln of x is equivalent to saying e to the y equals x, right? Because you just apply e to both sides, and then you get that, right? So that's what we've got. So one way to think about it is ln of x is the value such that e raised to that power gives you x, right? So a couple of examples, right? ln of e to the 10th, well, that's just going to equal 10, right? These guys cancel. Right, ln of e to the 17x, right, that's going to be 17x. E to the ln of sine of x, and then 5 ln of e squared, well, that's the same as 5 times 2, which is 10. Okay, just a couple of quick examples. What about, actually, here's one. Let me add a bonus one right here. What's ln of 1? Actually, no, let me add a couple more. What's ln of e? ln of e equals 1. Right? Because the power you need to raise e to get e equals 1. Here's another one. What's ln of 1? Right? It's the power you need to raise e to get 1. Well, that's going to be 0. What about ln of 0? ln of 0 is the power you need to raise e to get 0. Can you raise e to a power and get 0? No, you cannot. So ln of 0 does not exist. Similarly, ln of x for x less than 0 does not exist for the same reason, right? Because you can't raise e to a power and get a negative number. Maybe I'll just write that here. Because e to the y cannot equal 0, and e to the y cannot equal, I'll just say cannot be, yeah, I'll say just e to the y cannot be less than or equal to 0. All right. So what is the domain of the ln function? ln has domain 0 to infinity, the open interval from 0 to infinity, right? Meaning we do not include the endpoint 0. But sometimes when we consider ln in its own right, just not just as an inverse function of e to the x, we do want to expand the domain as much as possible, and so we throw in these absolute value signs, right? So that negatives become positive. So the domain of the ln of the absolute value function, or maybe I'll just call this f has domain negative infinity to 0, again, open interval, because we still can't consider 0, right? 0 is still a problem, right? And of course, if you want to shift it, right, ln of x plus 1, right, then the domain is everything except negative 1, right? That sort of thing, right? So then the other question is, what does the graph of ln look like? What if you expand it to the absolute values? And this is definitely worth knowing. So here are our axes. Now, we should remember that the function y equals e to the x looks like this. This is what exponential functions look like, right? They're very small when x is negative, right? Because it's 1 over x to e to the positive. But then at 0, we get 1, right? Anything to the 0 is 1, right? And then after that, the function really skyrockets. Now, ln is the inverse function. Now, do you remember how inverse functions work, how their graphs work? The way that it works is that inverse functions the graph of inverse functions reflect about the line y equals x. So if you just kind of turn your paper diagonally and reflect it, you get this. Well, let me try that a little bit better. Something like that. Okay? So notice it's the reflection of y equals e to the x, right? Now, what if we included the absolute value? Well, all we're doing there is we're just reflecting this about the y-axis. In fact, this is what happens anytime you consider f of the absolute value of x. You just get a reflection about the y-axis. Right? It's, to be clear, it's both of these, right? Let me actually... to be clear about that, right? All right, so we have that. And we do have a vertical asymptote. Regardless of whether we're talking about the absolute value or not, x equals 0 is a vertical asymptote, right? Because we're not allowed to plug stuff. We're not allowed to plug in 0, right? And note that the same way that that e to the x gets really, really close to 0 as x approaches negative infinity. As x approaches 0 for ln approaches negative infinity, right? So just something to keep in mind. Those are definitely graphs you should know. Now, what is the derivative of ln of x? Turns out it's 1 over x. And you might be saying, wait, isn't that a power rule or something? No, you can never take a derivative using the power rule and get 1 over x, right? X to the negative 1. It would have had to have been x to the 0, right? Not a thing. Now, the derivative of ln of the absolute value of x is the nicest thing possible, given that the derivative of ln of x is 1 over x. Pause the video, see if you can guess. Turns out the derivative of ln of the absolute value of x is 1 over x. Including the absolute value signs actually doesn't change the derivative at all. It's very, very nice. I'll prove the first part. I'll prove this guy right here, and I'll maybe leave the second part to you. It's actually very short, so you are responsible for this. It'd be a little challenging on an exam, but I actually don't think it's all that bad. It's similar to the inverse trig stuff, but not nearly as bad, right? Let y equals ln of x. Well, we don't know anything about y equals ln of x, right? So we have to say, okay, so if we apply e to both sides, we get e to the y equals e to the ln of x, which is x, right? So that means that e to the y equals x. Now implicitly differentiate. And you get e to the y dy over dx equals 1. Or dy over dx equals 1 over e to the y. Well, remember, we have another situation here where our answer is in terms of y, but we really want it to be in terms of x. But wait a minute. We know that e to the y equals x. So actually, our answer is dy over dx equals 1 over x. Done. Now, for the absolute value, you just consider the same thing. You just need to consider it's ln of negative x when x is less than 0. And it works out the same way. Dy over dx equals 1 over x. Okay. So that's the proof, right? That's the whole proof. Just a basic implicit differentiation problem right there. Okay. So now that we know that, let's do a couple of derivatives. Well, we have f of x. F prime of x is going to be 1 over the inside, right? Leave the inside the same, times the derivative of the inside. Right, if you want to simplify that, then of course you can, and should if it's not too much problem. Okay? Here, nothing lovely, right? We have to use the quotient rule here, low, d high, minus high, d low, all over low squared. And this is kind of nice. We can actually simplify this a little bit, right? We've got x squared times 1 over x is x. So we actually have x minus 2x ln of x all over x to the fourth. And we can actually cancel a factor of x, right? So you wind up getting 1 minus 2 ln of x over x cubed. And this is kind of interesting. Here, f prime of x equals, so it's ln of the absolute value. Now remember, don't worry about those absolute values. It doesn't change the derivative. It's going to be 1 over x to the 7th times the derivative of x to the 7th, which is 7x to the 6th. Well, that actually gives us 7 over x. But that's kind of interesting, right? Because that would be the derivative of 7 ln of x. So that suggests that ln of x to the 7th equals 7 ln of x. Really? Really. Fact 4 contains a bunch of very important log rules. Number 1, y equals ln of e to the x. Oh, sorry, that's actually a typo. I regret this. That is not what that is supposed to say. That is supposed to say y equals ln of x is equivalent to e to the y equals x, right? Raise e to both sides. All right, ln of a times b equals ln of a plus ln of b. So if you have multiplication on the inside, it turns out that splits over addition on the outside. Very cool, I think. And as you might imagine, division on the inside leads to subtraction on the outside. Right? These, by the way, are just consequences of exponent rules, right? The idea that, if you multiply two things with the same base, you add the exponents. If you divide, then you subtract the exponents. This is just another way of saying that. Excuse me. Number 4 is something also exponential, if you think about it, but maybe something you wouldn't quite expect. ln of a to the b winds up being b ln of a. All right, so that b just comes down right in front. Very, very nice. Okay? And last but not least, e to the ln of x equals ln of e to the x, which equals x, right? They're inverses. One other one, you don't need to know this, but I'll just put it in for completeness, is that, I guess I'll write it this way. For the scientists out there, the hard scientists, log base b of a equals ln of a divided by ln of b. Now, again, we won't ever use that because we don't really care so much about log base another number, but just so you know. So in other words, ln is the only one that you really need to know. in case you're like, oh, I'm a scientist, I use log base 10 or log base 2. Yeah, you could translate that into ln, and it'll be fine. Anyway, a couple more practice problems. Now here, this looks pretty gross, but using log rules, we can make this a bit more palatable, right? Now, unfortunately, ln does not split over addition, but it does split over multiplication. And so that's a bit nicer. Right, so we have 1 over x to the 5th plus sine of x, and then times the derivative. I'm just going to do it right here. 5x to the 4th plus cosine of x. Right? Just put it right on the top. Why not? And then we're going to have 1 over e to the 7x plus 2. Right? We leave the inside the same. Times the derivative. Right? And that's going to be 7 e to the 7x. Right? That's our answer. Ooh, number 2 looks awful. It's actually not that bad if you use log rules, right? We're going to get 3 ln of, I'll use just brackets. Well, maybe I'll use big parentheses, whatever. 3 ln of 1 plus 7 x to the 9th minus ln of x plus 8, right? I didn't take the derivative yet. I just used log rules, right? But I brought the 3 down in front, and I split the division over subtraction. Okay? So now, dy over dx is going to equal 3 times 1 over 1 plus 7 x to the 9th, and that's times 63 x to the 8th, minus 1 over x plus 8. Of course, the derivative is 1. If you want to simplify that, then you can. 129, no, 189 x to the 8th, 1 plus 7 x to the 9th, minus 3 over x plus 8. All right, you get that. All right, number 3, somehow looks worse. It's not that bad, right? Remember, the square root is just x to the 1/2, right? It's just raised to the 1/2. So take that 1/2 power and bring it out in front of the ln. Oh, and then, by the way, split that division over subtraction. All right, and then we get, what do we get? Right, so we're going to, so f prime of x is going to equal 1/2 times 1 over 1 minus x squared, but that's negative 2x minus, and then this is going to be 2x over 1 plus x squared. Right, and then if you want to simplify this a bit more, which we should, because this is not so bad, negative x over 1 minus x squared, negative x over 1 plus x squared. All right, done.